All right, so recapping what we learned in the first portion of this exploration is that when you are trying to integrate, that one of the things that you're going to be looking for is looking for something that is the known derivative where chain rule was used. Now, I will say that integrating, I kind of liken it to, it's a little bit of an art form, and it's a little bit of a puzzle where you're trying to make sure that you have all the pieces correctly put together so that you can reverse the process and find an antiderivative of that. And so the key idea here, and just to kind of remember, I'm going to really, really stress this, is that when we were working backwards and we're trying to make sure that we have the derivative of the stuff part of the chain rule in the integrand, that it's okay, we saw right here, that we can be missing part of the derivative of the stuff if all we're missing is a constant. We can always correct for a constant missing. However, if we are down here where we were missing, where it had a variable missing right here, you cannot correct for that. You are not going to be able to integrate that using the reverse of the chain rule. Okay, so I just want to really, really stress that part of the art of integrating is recognizing what stuff was the, quote, inside function and what the derivative of the inside function is. And if there's a constant missing, we can add a corrector constant by multiplying by a form of 1. But if there is a variable missing, then that's a no-go. It's not a chain rule problem. All right. So let's take a look at a slightly more complex integral. And we're going to apply the patterns above, but we're also going to start identifying how we're going to use this, quote, U substitution that's there. All right, so what we're basically going to do is you first identify the inside function. So we did a lot of this back in pre-calc as well, so hopefully it's fairly obvious to you. You're going to look at it and be like, hey, inside of a cosine is this x squared minus 2. So we recognize that we have a cosine function. Cosine is a known derivative, and that's kind of the key here. Cosine is a known derivative, and we have an inside function. So we're going to let u equal x squared minus 2. So we identify the inside function, and that's usually where our, quote, u substitution is going to come into play. Once we have the u, we're going to take the derivative of the inside function with respect to x. So we're going to take the derivative of u with respect to x, which is going to give me 2x. Now, I'm going to tell you that in a lot of the problems that we do for this, because we are integrating, we typically want to think of this not in the derivative form, but in the differential form. So I'm going to think of it as du equals 2x dx when I look at it. And when we are going to do our, quote, substitution, then this is what we're looking for to replace du with. That's what we need to have in our integrand as the derivative of the stuff. Now, when we look at the integrand above, we see that we sort of have it, but not quite, okay? So as we're looking at it, we'll say almost. We have the variable, we have the x, but we are missing the constant 2. And remember what my key idea above was, you can always correct for a missing constant, but you can't correct for a missing variable. So this is actually good, okay? We almost have it, so we're going to be able to correct it, okay? So we need, why is it important? We need the derivative with respect to x of the stuff in the integrand. And it's important that we are almost there. If you don't have the derivative of the stuff in the integrand, you want to make sure that only missing a constant is okay. It would be great if it was all there, but okay if it's only missing a constant, because we can correct for that. All right, so here's how you're actually going to show the work for this. Pretty much what you're going to do is you're always going to write on your paper the u and the du. Now, typically when I do that, I'm going to come over here on the side because I was explaining it here. I would have said u equals x squared minus 2, and then I go straight to the differential form and write it like that. So somewhere on my paper, you would write that down in a thought bubble over on the side. All right. Then you take your integral, and I'm just going to show all of the work in the string here so that it's very clear with my linkage, because you do have to worry about linkage with these. So that's what we started with. Now I typically reorder it so that I have the outside function, your inside function, and then I put the derivative of the stuff at the end. And because I've already done this part up here, I clearly recognize when I'm missing something. So you see how I left a little bit of a space right here where I'm going to insert the missing constant. But you can't just put a 2 into the integrand. That changes the problem. You can only multiply by a form of 1. So I add a corrector on the outside to the constant that I added on the inside. And the reason that this works is that 1/2 times 2 is equal to 1. And so it is actually just multiplying by 1. So we multiply by a form of 1. The needed constant goes on the inside. The corrector constant goes on the outside. Now, from there, what we're going to do is we actually do a U substitution. This is kind of important, especially for you guys, because it helps you see what you're actually taking the antiderivative of. So the 1/2 is now going to ride along. Let me change back to purple here. So we have the 1/2. We have our indefinite interval. We have our outside function, and then this is where we start substituting. The cosine, the x squared plus 2 is going to become our u. So it becomes cosine of u. And then let's do orange for this. Our 2x dx that we have here becomes du. So we substitute in so that now we are revealing what we're actually taking the antiderivative of. And then we just do our normal antiderivative. The antiderivative of cosine is sine of u plus c. And then we always finish the problem by actually going ahead and putting the u back in, because your final answer needs to be in the variable that you started in. The u substitution, just like when we did this back in pre-calculus when we were doing some problems, is really a placeholder to help you simplify the problem and reveal what antiderivative that you need to do. So the rewriting is this part right here. So we would rewrite to get it into its u form, which reveals the antiderivative, and then we find the antiderivative that we're doing. Let's, I guess, do pink here. The find the antiderivative is this portion right here. And so one of the most common mistakes that I see with students on this type of a problem is you get so into the making the u substitution that a lot of times you guys actually forget to actually take the antiderivative. So you do want to make sure that you do that actual step. Not only do you do the u substitution, you remember the point of the u substitution is to find an antiderivative, and then also make sure that you finish it up and put the original variable back into the problem. All right, let's go to the next page and let's summarize our steps. All right, so taking a look at this, the idea that we have here is that when we are integrating, let's first do a recall, and this is just a recap. If I let y equals f of g of x be a composition, where I have an inside function and I have an outside function, where we can think of the u, let me say where u equals g of x, the inside function. That when we are taking the derivative of that type of a composition, composition requires chain rule. And so when you take the derivative of f of g of x, that what you need to remember is that you always have to have the derivative of the stuff that's inside tacked on as a product on the outside. And I've showed it to you in both ways, where you have f of g of x. So I have g with its derivative on the outside, or f of u, where when you go to take the derivative of u, you got to remember that you have to take the derivative of u with respect to x. So that's the first kind of recall thing there. The second thing that I want to recall before we get to the actual whole integration thing is that when you take that derivative of y equals f of g of x, you're going to get dy dx equals your f prime of g of x times g prime of x. That we typically prefer to put it in differential form before we integrate, because the working backwards part was to rewrite it in that differential form. So if we rewrite these known derivatives of chain rule into their differential form, then what that is telling you is that when we look for an integrand, like how do we know that we're going to do this chain rule or U substitution method, we're looking for an integrand that is of that form. So when the integrand looks like it would be a chain rule problem, we can use U substitution to integrate. And we can use that U substitution when we are of the correct form, and the only thing that we can be missing is a constant. So taking a look at this, just kind of highlighting each of the components. I did all of the work in this middle section right here. Let's highlight that maybe in this color. So this is the actual work of showing that we identify our inside function, which is g of x. We take the derivative of g of x. I guess I should say, I said u equals the inner function of the known derivative, and that would be your g of x. You take the derivative of that known function with respect to x, and you put it in its differential form. And if needed, if you are missing a constant, then you would multiply by a form of 1. And remember, that's the only thing. It's only a missing constant that you can correct for. Nothing else. If you're missing a variable or anything, you cannot correct for that. You can only correct for a missing constant. You can add the missing constant to the integrand and put a corrector on the outside. Okay? So it's the corrector that's going to be the important part of that. We then would typically rewrite in terms of u. And once you rewrite it in terms of u, I'm going to highlight this because for some reason people forget this stuff. After you rewrite it, make sure you do find the antiderivative of the known derivative that you just rewrote it in terms of, and then rewrite it in the original variable. All right, so kind of keeping that in mind, I said this is going to take some practice. And I noticed, it was more that when I was doing the notes for this, that I realized that you need a little bit more practice than what's in this note packet that I gave you before we went on this hiatus that we're on. So what I would like you to do first, okay, is we have this check your understanding, questions 1 through 6. Give it a try, see what you can do. Make sure that you show for each one what your u equals, what your du equals. Okay, and I like to put these in a thought bubble, so we'll just put them right there. And then show your u substitution. If you need to correct, show that in a step in the center, like hopefully you'll see in this one that you are going to need to correct. So you would have a step where you have the integral, you have your 3x minus 4 to the 5th, make a space, and you guys are going to add in here and here a corrector. So add a corrector if needed, okay? Then what you are going to do in your linkage here is after you do that, you are going to rewrite in terms of u, right? So the integral, whatever is here, and then make sure you end up with your du there. Then you are going to take the antiderivative, and then the last step is rewrite in original variable. So you're going to do that, okay? So you're going to do that for each of these going down. And then what I would like you to do before you actually check your answers on that, because I might want you to come back to this. I felt like we needed a little more practice on the different types that you would see. So I added in here into your practice an extra worksheet here called Extra Practice with U Sub. And so I would like you to right click right here, download, and try and watch the video that goes with that. That'll be the third.